Hello everyone, welcome to the presentation of our paper. This paper is a joint effort of the Whale Lab of Tongji University and Thyssen U2 Lab and has been accepted by CVPR, aiming to improve the coupling optimization scheme of the parameter updating and label correction in existing meta-learning-based noise label learning methods. The meta-learning-based method generally assumes that the cleanly labeled validation set is available to assist in the loss reweighting or label correction of the training sets. And as shown in the middle picture, the validation and the training sets are denoted XVYV and XTYT respectively. Then we take the two coupled optimization-based methods MLC and MSLC as an example. And we can see that the general framework can be summarized by the structure shown in the middle picture, where the updated network parameters are used for updating the training set labels, with the loss on the validation set, while the updated noise set labels are then in turn used for network parameter updating. We think such an update scheme will make both the extracted features of the background network and the updated labels affected by noise samples, and thus neither of them can obtain the optimal solution. Based on the motivation, as shown in the figure below, we try to design the coupled optimization scheme between the network parameter updating and the label correction, where the background network is trained in a self-supervised manner and fixed during the label correction process to elevate the negative influence of noise labels, and the label correction is performed individually in this way. We further verify the advantages of the decoupled approach over the coupled ones with experimental results. Specifically, like the figure above, we trained the MLC and MSLC in a decoupled manner from the 70s epoch. For example, fixing the weights of the background network, and we can see that both MLC and MSLC have significant improvements in label accuracy and feature quality. In addition, we also load simply self-supervised weights in MLC and MSLC for coupling and decoupling training to demonstrate that the accuracy improvement does not mainly come from the pre-training weights, and we can see that the decoupling approach can also achieve more significant improvement in this setting. So we can conclude that the coupled meta-learning label correction scheme leads to suboptimal results, and the decoupling approach can effectively solve this problem. Next, we introduce the decoupled optimization framework Dmlp, which contains two main modules, IPC and EAC. Specifically, the background network is first trained in a self-supervised model and fixed. Afterwards, the training samples are fed into the background network to obtain features. Then the features are input to the linear regression model in the IPC to get the optimal parameter for the classification of the training set. Then, according to this parameter and the features on the validation set, we can perform classification on the validation set. Then the discrepancy between the clean labels and the prediction result is used as the loss function to directly update the training set labels. For the EAC module, it contains a linear classifier that uses the training features as input and use the updated training set labels to train with cross-entropy loss. The training set labels are updated periodically with its prediction results in this training process. To sum up, the optimization object of Dmlp can be denoted in the following form, which is to minimize the loss on the validation set, and since the training features are fixed, we can obtain the optimal classification parameter on the training set by solving a least squares way. Thus, since the value of the parameter is only related to the noisy labels, we can update the noisy training set labels directly with batch gradient descent. However, since the IPC updates labels too slowly, we further exploit the inherent robustness of the single-layer classifier to noise labels by using the prediction results of a single-layer classifier on the training set to periodically update the training set labels in the EMA manner to accelerate the label updating process. On the left is the procedural code of the method. As for the experiment part, we conducted experiments on both simulated noise setting and the real-world noisy dataset. The above results are the comparison of our Dmlp with the existing methods on the symmetric and asymmetric settings on the CIVA 10 and 100 dataset, and we can see that Dmlp naive method also achieves a very significant performance improvement compared to the cross-entropy, and our method can also bring a huge improvement to the dynamics when combined with it. In addition to simulated noise, we also conducted experiments on the closing 1M dataset, and our method has significant advantage over existing meta-learning-based noise label learning methods. And specifically, our Dmlp divided mix can achieve 78.23% accuracy, while Dmlp naive can also achieve better performance than existing methods, even though it is only trained with cross-entropy loss. In addition, we combined the pseudo label generated by Dmlp with 3 popular noise label learning methods, including cognition, CDR, and ER+, and we can see that our method can bring a huge performance improvement to the existing methods, especially in the high noise cases. And we can also perform the same performance improvements on the CIFAR10 and the closed 1 datasets. We also individually analyze the effects of IPC and ESA module on CIFAR10 and closed 1 datasets, and we can see IPC can effectively improve the overall performance, while ESA can also improve accuracy with its inherent robustness against the noise. And since our method demonstrates the result of combining with divided mix, we also make a fair comparison by combining the coupled optimized methods MLC and MSLC with divided mix, and we can see our method can also achieve superior performance to them. And this is the parameter sensitivity experiment, and the results show that our methods are not sensitive to all these parameters. We further visualize the accuracy curves of Dmlp divided mix and divided mix CDR, divided mix CDR, and CDR trained under multiple noise settings, and our methods has obvious advantages over benchmark methods throughout the training process. And when combined with cognition method, our method can also bring very significant improvements, especially in the high noise cases. Finally, we also listed the results of MLC and MSLC when loading self-supervised weights for coupled training and loading self-supervised weights for decoupled training. And our naive methods also achieve better performance than them. And that's all we worked on. Thanks for watching, and our code will be open sourced at the following link, so feel free to follow along.